For those of you who do not know me, my name is Ali Kujuri, and I'm one of the organizers of this lecture series. Let me also thank Mr. Sharon Marivani, and also Ronnie Goodland, who helped me in setting up these lectures. On behalf of the department and the School of Science and Technology, let me welcome you all to this second lecture of this academic year, or the 113th lecture in the series since 2009. It's good. Now, before I introduce our guest speaker, let me make two little announcements. First, the pizza that we have ordered will arrive at 5:30. Be ready for that. And then also the next lecture will be on October the 6th, titled Internet of Things Based Environmental Monitoring System by Mr. Shiva Kumar Matapati, and he's the co-founder and CTO of New Mobility. The guest speaker for today is Mr. Sean Headrick, and the title of his talk is Unmanned Aircraft System in the Coming Robotic Revolution, the First Wave of Attack. Mr. Sean Headrick is the CEO and co-founder of AeroTestra, which he has started in 2012, and is proud to be an advocate for and contributor to the exciting robotic evolution we are experiencing today. A self-taught designer and engineer, he spent the majority of the past 25 years designing and building everything from cabinets and furniture to tree houses, and all variety of things in between. His current project, developing unmanned aircraft systems, has tapped into several passions at once that he hopes to share and learn from his ever-growing community. I met Sean, by the way, early last spring in one of the exhibitions, in fact, at the Student Center, and I was really amazed to hear that he has done all of these things that you'll see very soon, all by himself through research and basically self-learning. And really, that's really amazing to see that somebody will do all of that. And the self-learning and also research, as you know, is what characterizes the inventors and also innovator. So here is Sean.
Thank you very much, and thank you for that introduction. That was nice. So yeah, like he said, I started this company about 4 years ago. And essentially the idea was just to be able to, really the idea started as building an autopilot system. I just kind of gotten introduced to the Arduino. I'm sure you're all familiar with that, and understood sort of the rule base of that, and wanted to fly remote control airplanes, but knew I had no technical skill to do that. And shortly realized that there was an open source autopilot program known as ArduPilot that has several branches to it: ArduCopter, ArduPlane, now there's ArduRover, ArduSub. So basically any type of vehicle can be powered by this autopilot system given the proper firmware. And so the first thing that I kind of got into was the multi-rotor aspect, and very quickly just started to get this overwhelming idea of all of the different things that could be done with it. And video was not really the first idea, although that cinematography has really kind of risen to the top because it is really possible to make awesome looking videos with these platforms. But, you know, just the ideas of being able to have a vehicle that could go to a certain place and perform any kind of action, perform an action or collect some data. Disaster response was right there at the beginning. I thought to be able to go and create an aerial image of a disaster area just minutes after it's happened and upload that to the web was just, you know, all of these ideas were just bubbling up in me. So the idea of self-learning or the research was just my roadblocks to being able to do that thing that I was determined to do. So it does kind of take that passion, I think. So it's important that you, I believe, in your journey, decide what you're passionate about, because oftentimes that's going to be the one thing that's fueling you or propelling you forward. It's very hard to just keep pushing without some kind of fuel like that. So, you know, kind of keep that in mind. And so I'm going to tell you a little bit about the sensors that we use, the way that we apply them, some of the other ideas that have been working out in the space. I know a few of you were here yesterday, and this isn't the same presentation, so don't worry. This will kind of go into a bit more detail about some of those areas and about some of the design challenges and problems that we were developing solutions for along the way. And then at the end, and really in between, if you have just a question that's burning you up, feel free to raise your hand, and I'll I'll respond to that. But at the end, then we can I'm happy to answer any questions you have. So the title, Rediscovering Our World. These systems are going to be all over the place in the coming years, doing all sorts of things, but collecting data, is going to be a big part of it. But at a different scale. So now we're going to be looking at the world in millimeter precision as opposed to satellites that looked at the world in meter or 10 meter precision. Now we're getting down to, the width of a pencil is the ground resolution. So for that, what we're talking about is photogrammetry, or structure from motion. And we're all probably pretty familiar with this just based on Google Earth or Google Maps, how you have a 3D topography that's illustrated there. That's basically multiple images from multiple satellites. So if you take these camera positions as satellites, each one can detect identical features on the ground. And then by looking at that same feature from multiple positions, instead of it being a 2D image, you can interpolate a 3D image. So that exact point is given an X and a Y and a Z coordinate. And so if you take a single image, if you take a single picture, then it's looking at the pixel, and it's looking at the pattern around that pixel to discern that is the pixel that's in multiple photographs. And from that, it mathematically calculates the way that it's been done for many years. Photogrammetry is not a new science. Structure for motion is sort of the algorithmic, or the having the processing power applied to photogrammetry. And so this is kind of the next phase. And so if you can understand, I think I explained that pretty well. That is structure for motion. The type of sensor that we use for this, and we have one in this vehicle because it is designed for this type of application for aerial mapping, is just a high quality camera sensor. So this is a full camera in here. It's a 1-inch Exmor CMOS sensor, so it's basically a CMOS sensor, but the Exmor prefix is the way that the CMOS is layered. It reduces noise in the image. So when you're looking at each pixel and trying to build a topographic map from that, the reduction of noise in that image is quite important. And so we're always trying to define these optimized features for this type of data collection. And what you can see also is that it's gimbal stabilized, and it's also vibration stabilized from the body of the aircraft, because there's going to be vibration. Even if everything is balanced, just the chunks of air that are being pushed into the body are going to create a Z vibration. And so you have to deal with that, or you're going to get blurs in the image. The higher your resolution, the stiller you need to be, right? Because if you vibrate the width of a pixel, you've lost that pixel's resolution. And then what is the data that we collect? This is essentially what it looks like. So it's just aerial images. And this is collected, I should say, the mission is planned using a user interface on your computer. There's Mission Planner, there's Q-Ground Control, and they're open source as well. This entire autopilot platform, the hardware was developed open source, the software is developed open source, and the user interface also. And so you can download that offline. And so we can describe an area of interest in a maps type interface, and based on the sensor that we have, the size of that sensor and the focal angle, it knows what the footprint of that image is on the ground. And then in order to perform that structure for motion, you have to have a high percentage of overlap and side lap between those lanes so that it can essentially align those photos. And so they're also geotagged. So as we're flying along, we're taking, every time the autopilot sends a camera signal to the camera to fire, which it's doing in a predetermined distance, about every 15 meters when we're flying at 150 feet. But that is also determined in that user interface based on your camera. So as you go up, the user interface will automatically space those points further apart because your overlap on the ground will still be the same. So as the camera sends these camera trigger commands from as the autopilot sends these camera trigger commands to the camera, it also notes the GPS location that it's currently at. And that typically refreshes at about 5 hertz right now. You can get some GPS that'll update a little bit faster than that, but that's generally the rate. So, we're triggering once every few seconds. So that's well precise enough to geolocate that image. And it's your lat, your long, and your altitude. So from that, we process that using a photogrammetric software. We use Agisoft Photoscan. There are a number of cloud-based softwares. But Agisoft Photoscan, that's kind of gotten to be the standard. That's what USGS uses. That's what a lot of our clients in the survey industry use. It allows you very precise control of what you're doing, how the material's being processed. And I should say, you can also apply ground control points to this model. So, and we'll actually get into that in just a moment as I show you an example of how this is used. But the resulting products that you get out of this, in the top you have an orthophoto. So that's an orthophoto that's geotagged that you can import into Esri or ArcGIS, other kind of geospatial information tools with like I said, about 5 millimeter ground resolution. So as you can imagine, that becomes a very large map if you print it at that scale, but it's pretty fascinating to see that as well. The other products here are a digital elevation model. So that is exactly what it sounds like. It's a model of the terrain. You hear it, you see it here applied with a false heat map that shows the highest sections as hottest and the lowest sections, which are actually at mean sea level here, as coolest. From that digital elevation model, you can generate contour lines as with a higher frequency as about 3 centimeters, and generally that's way too that's way too accurate or too high resolution for most survey applications. So they're looking at 1 meter slices of that contour. You can also define certain areas here, whether they be negative volumes or positive volumes. So like stockpiles, big piles of gravel. Say you have an area that has been excavated, and we're actually on a project right now where we're providing this information, and they need to know if the stockpile of material that they have here from the rest of the work site is going to be enough to fill that volume. And so we can tell them that quite accurately just from the aerial images and selecting that area of the map. We can give them a cubic volume down to the cubic meter. What you see at the bottom is ground point classification. So it's kind of hard to see, but it's the same as the top map. But what we've done is we've described that we want to remove all of the trees from the surface of the model. And so basically it'll take the ground plane, whether it's flat or curved like you see it is here, and anything that's, however you define it, anything that's over 1/4 meter off that ground surface is stripped away, and you've classified the ground surface as ground. You can classify roads, buildings. Buildings would be classified because they will typically encounter that ground surface at 90 degrees, and so you can create these rules that will help classify that. I think that's pretty clear. This is a project that was done by Sandus Civil Engineers down in San Jose. It's about 100 acres, and this would, what you can see here are the ground control points. That's what these little flags are. So this model would have an accuracy of about 1 meter, just using the geotagged images with no ground control at all. But once you put in the ground control points, you can bring the accuracy, not the resolution, but the actual accuracy of that model anywhere on that model down to less than 3 centimeters. And that's provided that your GPS, that your error-corrected GPS is also within that range. So it's not going to be better than what your GPS ground control points are. This entire area was geotagged, or these ground control points were put in place by 2 surveyors, and all 3 flights that it took to cover this area was done in about 6 hours. And they used about 24 ground control points on this model.
Sean, can I ask you a question?
Yes.
Now, what is the current resolution of the GPS? The ones that we have in our car and so on, we can just resolve probably maybe a couple of feet.
Sure.
Whatever. But then how about this? In this application, you're talking about, much smaller.
Absolutely. So there's different types of GPS, and then there's also ways that GPS can be, that data can be fused. So when you have a GPS in your phone or in a camera, the satellite reception is likely not going to be that good. So you might get, between 3 and 9 satellites, probably at max. And then it's probably just using a mean value between those. This GPS will typically get 20 within a few seconds of startup. And so based on that, it can apply Kalman filtering or some truth bias to try to describe where the most accurate representation of the GPS point is. Obviously the most, which is also a mean calculation.
Right.
With RTK GPS, or real-time kinematic processing, it uses a known GPS position and your GPS position out in the field, and it basically creates a correction value. So you can bring essentially what's a meter, and that's about what we're looking at now, is a meter resolution or a meter accuracy down to 5 to 3 centimeters. And so that's what you see your surveyors out there using is RTK GPS, and that's kind of an ever-evolving system. The ways that they can connect to broadcasts from these stations that are set up everywhere, but it's going to be kind of starting to be built into Wi-Fi. You can triangulate positions that way. So that space is always growing to where soon you won't really need that control station. You'll be using all the types of data that we get that'll be able to bring that type of accuracy. So this is sort of the market analysis of what this technology means to a major industry. So for traditional survey, would have cost about $20,000, and that employs 4 to 5 surveyors who are paid top dollar because it's a very long time and hard road to get to be a surveyor, and it's a good paying job. So you have 5 guys working 5+ days to lay somewhere between 4,000 and 5,000 of these high resolution points. So obviously they're limited by the terrain that they could cover here. You could see they likely couldn't cover a lot of these just because the slope was too high, the tree cover. This is an old Air Force site with that's a large radar tower that was used during the Cold War to detect planes coming in from Russia. So now this is going to be turned into a big green space, and this was a phase 1 study for that. What they probably would have resulted doing would be an aerial survey, a manned aerial survey. The resolution clearly wouldn't have been as high, not a major concern here. But the process for that, contracting the flight, getting the images from the flight to a service that would perform those photogrammetric processes, and then getting that back to the surveyors where they would still need to build these deliverables for their client, would be between 6 and 14 weeks at a cost of about $18,000 to $24,000 when you look at the post-processing in that. With the UAS survey, a piece of equipment just like this, they went out in the morning, they laid the 18 ground or the 24 ground control points, flew it in about an hour's time, 3 15-minute flights plus setup and breakdown, automated the 3D reconstruction through the software that I'm describing, which was done overnight. You basically register these ground control points and then you just let it run. By the next morning, everything was done. $4,500 in labor for those guys, and I mean, it's not hard to see how this is very disruptive technology. Precision Ag, did anybody have any questions about that first section before I kind of jump into a different area? Precision agriculture is another area that gets a lot of voice, and it's not really clear to a lot of people what that means. It's actually been around for a while. It's not just based on UAVs, but it's certainly been implemented by the use of UAVs because of their ability to both collect precise data and to geographically tag that data. And so it essentially means being able to apply the constraints of time and location to observations in agriculture. So you could often go out and see that you had, pests or water problems or these types of things, but being able to say exactly the geotag or the GPS point where that problem exists and to the scope or severity that it exists, and then to compare that with a point just a few inches over or a few feet over, it didn't exist before. And it was largely the experience of the farmer or the agricultural professional that would be able to make those decisions. But now we have where we can, looking at this is what's known as an NDVI, or a normalized difference vegetation index, and I'll get into that in just a minute. But it's essentially also a false heat map or an artificial heat map that describes areas of vigor or efficient photosynthetic activity relative to areas of less photosynthetic activity. And I describe it that way because it is precisely a measure of that. And I'll describe that in just a moment. The sensors that we use for this are the same. We're looking at 4 bands of light when we're trying to detect photosynthetic activity. 3 bands are your RGB, your red, green, and blue. Those are the visual range of light, and that's what plants absorb to carry out photosynthesis and make sugar or make energy. The other band is the near-infrared band. So that's a band that you can't see, but it's the one that would burn plants' leaves if it were absorbed, or it is essentially the band that is reflected when photosynthetic activity is being carried out most efficiently. So at the peak of efficiency of photosynthesis, the most red, green, and blue is being absorbed into the plant, and the most NIR or near-infrared band. And when I say near-infrared, this isn't thermal. This is as it's approaching that thermal region, that thermal irradiance region of the spectral wavelength.
Is that like 800 nanometers?
We're actually looking at 900 to 915.
Okay.
Yeah, right around there. 800 is actually what's known as the red edge. And those two wavelengths or bands, they're used kind of interchangeably in this field. The 800 to 815 right now is apparently very effective for detecting algal blooms. And then in different crops, you're going to have different reflectance values for that crop or for what it is you might be looking for. So you need to have at least 2 cameras, one that's collecting the RGB, or 2 sensors. They can often be employed in a single camera set. And so that's what we're creating, or that's what the data that we're collecting. What the data looks like is like this. So your NIR images are going to look like the ones at the bottom. I have to be honest with you. I basically took the top ones and modified them slightly to represent NIR images. But if these were actual NIR images, the crop rows you see here would be white because you're seeing that reflected near-infrared radiation. But this is generally the color scheme that they take. But yeah, you would really see that near-infrared radiation, and that would be evident in the post-processing. The RGB is actually RGB images. This is at Ryder, so Ryder does all the strawberries, berries for Driscoll's berries. So we were flying these sites. So now you have 4 bands represented here. For processing this, it's not nearly as straightforward as for photogrammetric processing. For that, you basically upload the images and you walk away. For this, based on what it is you're trying to define, this formula can vary quite a bit. But this is the basic formula for NDVI. And the goal, and I can just kind of describe it to you here, it's the near-infrared minus that red, green, blue, and it's divided by the near-infrared plus that green, blue. What that does, the difference in healthy and unhealthy without this exaggeration that this formula provides is very difficult to discern. And so what this formula does is basically it takes that very small difference and stretches it out so that you can see healthy to not healthy. And that would typically, what you would see it in would be a grayscale image. And then we can apply a false heat map to that grayscale image, and that gives us a much better way of visualizing healthy versus non-healthy. Another thing about this, irradiance. The sun can have a dramatic impact on what you see here. So if you fly the same field 3 days in a row and you vary the time or the conditions change at all, if you try to compare those day to day and say this looks healthy this day, but using the same formula and the same methods, it doesn't look healthy this day, it's simply not a way to do it. So you actually have to be able to take into account that irradiance, the time of day, a lot of other factors. And so that's where this is going to be a much more useful tool as we can apply it over time. We can have models from every day time-stamped and create larger and larger data sets to start to pull intelligence from. And that'll probably be done largely with machine learning processes and not by us just looking at the images. Now what you can see here is relative health. So that's quite helpful, right? A few different imaging payload options would be thermal. Search and rescue is obviously very important. These small thermal sensors can detect a human signature, a human heat signature at 300 meters. That's almost 900 feet, or it's 900 feet. We're typically flying at about 150 feet, so we could map, say, 40 acres in just a few minutes. And being able to detect a human signature in 15 minutes over 40 acres clearly would give us a head start in trying to find a lost hiker or, whomever it was that we were looking for. Moisture uniformity in crops. In that same image that you saw there, that was a vineyard in Napa. The name is escaping me, but as the sun was rising in the morning, heating up the leaves, we flew over the site and were able to see that, or were able to infer from the idea that as the temperature goes up, the leaves would become warmer relative to the amount of moisture that was in them. So leaves that had less moisture in them would heat up faster, and leaves that had more moisture in them would heat up slower. And would likely, well, not that they're getting that hot, would likely have a lower temperature, lower maximum temperature. Water detection for irrigation leaks or vector control, so looking for areas where mosquitoes might be, or leaks in the irrigation, and then livestock identification, counting. Heat signatures stand out like light bulbs on the surface of the ground. A cell phone it's amazing the heat that comes off of a cell phone. It's like a beacon. It's just interesting if you ever see it through a thermal camera. You can see it from forever away. We talked about what the sensor that we use in here. This is the sensor. It's a small barrel style camera. Everything from precision mapping, aerial photography, videography. The near-infrared method is approached by removing the low-pass filter on these cameras. So all of these cameras employ a sensor that can actually see in that near-infrared band. But if they didn't filter out that near-infrared band, then your pictures would look really strange. They would look abnormal because they're not what you see. So they put a filter on there that brings the sensitivity of that sensor down to just what we see. And so most cameras can be modified that way. There's a lot of open source projects online that allow for modifying a little webcam, uploading that imagery, and doing some of that processing online. And then there's hyperspectral sensors. So that's kind of like the near-infrared and the RGB. So with that, we have 4 bands that we can look at. This hyperspectral sensor has 320 bands, all that are discrete bands. So you can select one band and look at that reflectivity that's being imaged from that. So with that, you can essentially see down to the molecule. You can define what nitrogen is based on its spectral reflectance. Yes?
Clearly, when you put a spectrometer of that kind, it has advantages and wider band, but how about the power consumption?
This is the hyperspectral nanocube. So this is kind of the most advanced in the field right now, and it's about this size. The main problem with this is its memory consumption, because it's accumulating tons of memory. So we actually have to turn that on and off just over very small areas, but the power consumption is really quite low, especially relative to the power consumption of lifting this vehicle. So we're talking about 12 volts. You know, it's
So it's not heavy?
No, it's not too heavy at all. No, we actually were in a project just a few weeks back where we flew this sensor that the University of Hawaii has, and we integrated it onto one of these platforms, and we flew it at Hunauau State Park in Kona, Hawaii, to assess the coconut groves there. They're having trees just dying, and they don't know why. Boron deficiencies are a possible cause, but we were using this sensor to be able to look at the exact spectral reflectance and try to identify the difference between the healthy plants or the healthy trees and the trees that are dying long before they're actually dead. And just to kind of go back, you know, oil, gas, mineral exploration, to be able to see a mineral on the ground that either you wish to mine that mineral, oftentimes oil fields or other natural resources that are hidden from sight will have correlating mineral deposits on the top of the ground. So, you know, it becomes a very effective way at doing that type of exploration over very large areas.
Excuse me?
Yes?
Yeah. Do we need to make any correction when we are imaging during a foggy day versus a sunny day with any of these?
Absolutely, yeah. That's kind of what I was describing, where as the irradiance changes, it really changes the output of the information. And that's when you're looking at the relatively rough output of that of just the NDVI. With this hyperspectral sensor, the amount of calibration that has to be done during the flight, before the flight, is immense. We have to do, basically we're mapping in real time the change of irradiance on a perfectly calibrated white plate, to basically see what the change is in the irradiance of the sun or in the conditions at that point in time, so we can map that back to the time track of the information that's coming through this sensor. So since we don't have a controlled environment, yes, absolutely, it's very important to be able to, because that is our testing catalyst. That is what's providing the information. So as that would vary, what we get, the data that we get from the ground or from whatever it is we're sensing is going to change corresponding. So yeah, it is a problem, and it's kind of being worked out, and most of it is with a real-time irradiance sensor. So they have agricultural cameras that are being developed now that utilize a sensor on top of the aircraft to basically take the sunlight and make accommodations to the data that's coming in. Mm-hmm. But it's a hard variable to control, and it adds a lot of noise to the data. Other payload systems would be gas detection. Oh yeah, go ahead.
Oh, I was just going to ask, is there a mechanism for switching out like the sensors, or is each drone built specifically for an application?
The way that we build this equipment, each drone is built very specifically. And you caught me with drone. UAV is kind of the term I prefer, but we build these very specifically because often we're integrating in the characteristics of the autopilot as well as the wiring to the autopilot. So for that hyperspectral sensor, it's collecting so much data that we need to basically send a signal, a relay signal, a 5-volt relay signal from the autopilot every time we pass a barrier that we've defined. So if we've defined, an area like the top of this desk, as we fly over that barrier, a 5-volt signal is sent from the autopilot to the camera to turn that camera on. And then as we fly over the other side, it turns that camera off. And so then as we fly back and forth, we can send that information. And it's just most of our end users are not really qualified to get under the hood. It's anything can go wrong, and it often does when they do. If you understand it, then that's a whole different sort of story. But we really build this for the user that needs very reliable equipment and isn't really prepared to build that or configure that themselves. And and there's a lot that goes into that. So for that hyperspectral sensor, that's forward mounted. So we had to do some work to maintain the center of gravity for the vehicle itself. So yeah, to answer your question, we don't really have too many swappable options. But most of our end users are using it for a very specific purpose. A lot of things that could be added or other types of sensors would be for gas detection. These are typically very small sensors and could be logging data regardless of what the vehicles are doing. So if we had hundreds of these out in the field doing survey operations, they could be collecting data on air quality at the same time. And that could just be offloaded into a different database. Methamphetamine production is something that I was kind of interested in, not actually methamphetamine production, but but the detection of the gases that are present during methamphetamine production. So, being able to fly over and find that. And then spray migration, that's obviously can be quite toxic, and making sure that, I think an interesting idea is that given the characteristic of how these fly, in addition to collecting gas toxicity or air quality measurements, we could ascertain from the characteristics of flight based on what we know about the aircraft, what the wind is doing, the direction that it's flowing, just based on if we know that this has to pitch forward at 3 degrees to fly at 5 meters per second, then if it's pitched forward at 8 degrees and rolled at 2 degrees, then we can ascertain from that information the direction and the speed of the wind, right? And we can do that just with data that's already being collected on the aircraft and information that we know about the aircraft. Radio frequency identification and Bluetooth type applications. I've seen a couple posters out on the wall out here, and I know we discussed some applications where having a network of sensors on the ground where you could go out and collect that data. Also RFID tagging for wildlife and livestock, those type applications are pretty logical. You know, kind of what I'm describing is just about any sensor can collect data, can be put on this equipment. We lost this on the bottom of the page, but what we have is sound detection. So there are a couple kind of neat ideas here. We're working with University of Hawaii on another project where they have software that if you put in a recording of birds, it can tell you the type of bird and the number of birds that are in that recording. And so by flying over regions of the island and geotagging that recording track, you can basically create population maps of these different types of birds. And the idea would be to do vibration isolation of a directed microphone, because a lot of that noise would just come in through vibration through the aircraft and through the armatures that connect it to the vehicle. But to quiet that down to the point, and then maybe use some type of noise cancellation to just get the sound of those birds. The other one below that was gunshot triangulation. So you could have these vehicles dispersed in a city environment or in a theater of war, perhaps, and all of them interconnected. Once a gunshot goes off, instantaneous triangulation could occur through the vehicles, and then the vehicle could essentially move to that location and provide situational awareness, what's going on there. Let your imaginations kind of run wild with all of that. So what we start kind of getting into how we look at this data or how we visualize it or work with it as we move forward. We can start with the framework or the earth, the virtual earth that we can create with these through that photogrammetric process. So now we have a realistic interpretation of the earth as a digital model. We also have identified structures, power infrastructure, residential areas, industry. From that, we can start to apply these layers of data that we're collecting, regardless of what it is. If we can geolocate it, then we can place it in this model with some way of representing its intensity in scope. So this illustration is a bit abstract, but it's to give you that idea of layering that data. So we can start to add in air movement using kind of the ideas that I was describing there, where just taking information from the vehicle, we can ascertain wind direction and wind speed. We can look at air toxicity or air quality generally and know how that air quality might migrate from area to area, from industry to residential, how we might be able to make greatest use of wind turbines and that type of equipment, so planning. Really any kind of data that can be measured, even data from the ground, so people's Fitbit data could be interesting to employ into this model. If you have everybody across this area, you'll have a mean fitness level and a mean cardiovascular level. And if you could compare that to air toxicity, then that would be, an interesting correlation to make, right? I'm sure that every type of data that could be put in here would have some interesting output if it were measured and analyzed correctly. So then when we kind of take it out of just our own hands and start to apply constraints to it or constants to it that give it more of a laboratory setting, now we can, we already know our time and position of all of this, so we can have it on a timeline. We have it on our digital Earth model. we can start to create that laboratory environment by correcting for ambient light conditions. So for that near-infrared or the multispectral imagery, we can start to apply over time what we knew the sun position to be, relative azimuth and declination and all this, the background noise of any type of sensor data that we're getting, and then start to establish standards about how this is measured. This has been done forever in the laboratory, but now we're moving that laboratory out into the real world. This is the scanner, and the Earth's surface and the surface just above it, or the area just above it, is the lab bench, right? So we can apply those standards that have already been built in the lab to these models. And then we can kind of use machine learning. We're already seeing that a great deal. I was just talking with someone yesterday about something they recognize in their car, that when they get in their car at a certain time of day, it pretty much knows where they want to go. And that's kind of fascinating to me. It's this smart GPS. So if you get in the car around 5, it's either going to be the first or second option in your GPS. You either want to go home or you want to go this other place that you go every day at this time, or however the pattern has been recognized by the software. So what the software can do is recognize patterns that we simply couldn't recognize, either because of the inconsistency of it, the scale, the sampling, for any reason at all. But machine learning can start to pick out these patterns quite efficiently. From that, we can define what we decide are the most optimal conditions or the best results, and we can look at that data and understand how to either change our behavior or act proactively to create the best environment, whether it's not to build a school downwind from the industrial facility, because we have this data to do that planning. And then when we start to look at it over cycles, whether it be years or multiple years or even decades, the predictive intelligence is going to be something that we've never had before. We've had it in a pretty rough scale, but when you apply machine learning to this resolution of data, it'll be, I believe it'll be quite amazing and quite impactful on the way that we plan and move forward as this technology starts to take hold. So then we kind of get into what the equipment is, what the engineering challenges are to building equipment like this. I don't know. I know one person for sure has been doing some work with UAVs. Any, not too many? Yep, you're the one I was talking about. They are essentially erector sets right now. The level of quality of build is really determined by the individual building it. And so to expect that it could live up to the conditions that we expect for this equipment to live up to, it has to be built more from the aircraft side down as opposed to from the hobby side up. So what we've really done here is we've miniaturized aircraft design and the protocols and the methodologies that go into building high quality aircraft. So part of that is duty ratings versus the requirements of the vehicle. Most of this equipment is running at somewhere between 10 and 12% of its overall capacity. You can already imagine how that'll have a tremendous impact on the wear and tear of the vehicle over time. In addition to kind of increasing the scope of where this can operate. So the University of Hawaii is using this equipment at the top of Mauna Kea. That's 16,800 feet mean sea level. Most other vehicles don't even operate up there, but this equipment does, and I believe it's based primarily on this one component, which is that we build this equipment to operate at a very low capacity relative to, or at a very low need relative to its overall capacity. Maintenance procedures are a big part of this. We have a long document that our pilots in command go through every time they operate this, every time we maintain it, every time we build one. We have a long checklist. It's an important thing for anybody getting into this, any kind of aerial vehicle. You need to be on top of everything that can go wrong, because one thing that goes wrong will bring these things down. Certified technicians, really nobody works on this equipment but us. So whenever anybody has a problem, they send it back to us and we repair it, we certify it, and we send it back. Any type of upgrades, they send it to us, we repair it, we send it back. When we look at the aircraft design itself, a lot of that is really my invention. It's what I've come up with through the past 4 years of developing this design, which has gotten tremendously complicated over time. It started out as much simpler than this, but these small requirements build up, and you build these solutions to them, and those solutions build on, and in the end you have something that looks a lot like this. It started out with this unibody design, and so when you look at most multi-rotors, you'll see that they're built out of plates and booms, or kind of a skeletal type structure. And inherently a skeletal structure just is very fragile. At the point where connections are, the entire weight of the aircraft is obligated to that, or that connection is obligated to the entire weight of the aircraft, and you add inertia or momentum, and it's going to break once it flies. This really doesn't. I mean, the stories I've gotten back on what this structure can endure is impressive. 30-meter falls without any kind of damage. And that's not to say that it can do that all the time, but you get kind of the idea of what it gets down to. The wiring harness design, basically every part of it has to be designed and iterated to identify any possible failure. Power supplies have to be designed. You often have multiple different sensors and pieces of hardware in there working simultaneously, and they all will need a different power supply or filtered power depending on what type of equipment they are. RF shielding, you have multiple radio frequencies operating simultaneously, so you have to be wary of that, or you have to be aware of that, I should say. And sometimes RF shielding is a requirement. You have compasses on board that are very sensitive to electromagnetic interference, which you have for large magnets on the vehicle as the motors. So being able to create a quiet space for that compass to operate is primarily important to its ability to navigate. Heat dissipation, obviously, with the equipment running, you need to understand how to deal with that. That's also dealt with the duty rating relative to the operational requirements. If you're operating at a very low percentage of the maximum capacity of the vehicle's power system, then heat isn't going to be much of a problem. If it is much of a problem, then you probably have some imbalance there. Ingress protection, these need to operate in any kind of weather, and these can operate in any kind of weather, because that's been addressed. The autopilot, everything is rated at essentially an IP67, where it can take any type of weather, wind, really no problem. The motors will run submerged. So water is not a problem for three-phase motors like this. And then sensor vibration and isolation. I showed you the camera. That's pretty important for the sensor data that you're getting. But when you get into the autopilot, it's incredibly important. Vibration can affect its accelerometers to where they're practically useless. So you have to create an extremely quiet environment for that autopilot system to operate efficiently. And so these are all things that have to be thought of with every change. The idea, I think, is always to be improving these things, because if they can be improved, that's a lower chance of failure. And a failure with commercial platforms being operated where they are is kind of a catastrophe in my book. So these are some of the different platforms that we build out for dedicated applications. The one you're looking at there is this one. So for aerial mapping and survey, the design requirements here are that it be able to cover large areas of land. So this will operate for 20 to 22 minutes, which gives us a coverage of about 40 acres with somewhere around 1.5 centimeter ground resolution. And that's plenty high for what most survey applications require. High wind tolerance. These can operate in 30 knot winds plus, and that's mainly the reason that we have the gimbal is so that as you're flying at 30 degrees bank angle to hold direction in an oncoming wind, your camera is still facing directly down below you to provide nadir imagery or bird's eye imagery of the area that you're trying to collect and that you're geotagging that photo for. And then portability, you can see how this all breaks down into a small case. Most of these systems you see would kind of take up this whole tabletop here, and portability is not really something that's been thought of. So that's kind of always the case, is that everything needs to fit in here. So you have your aircraft, your control mechanisms, your radio links, batteries, really everything you need besides a laptop to plan the mission. And we just kind of expect people to carry that with. This is the same platform, but it's been designed for industrial inspection. Bridge inspection is a big interest. So what we've designed here is an articulating camera that's mounted on the front of the vehicle that can look directly up all the way down to nadir, or directly facing down, with no propellers in the image. So if you were trying to inspect the underside of a bridge, the side of a cell phone tower, something like that, it can accommodate that. It gives 360 viewing capability, given the yaw capability of the aircraft that it can turn. So you can create an entire sphere of images from this platform. Again, the high resolution camera. Range detection, because for this vehicle you're looking at trying to be able to maintain a given distance away from the object that you're inspecting. And then GPS denied functionality. There's a lot of people working on that. For this, it's more a characterization of the autopilot to rely more on dead reckoning methods as opposed to GPS data that's coming in. So it's relying more on the accelerometers to understand where it is instead of the GPS data, because under a bridge you're not going to get great GPS data, or it's going to be multipathing, so it's going to be erroneous GPS data, and so it'll be very hard to hold a steady position. But if you cancel out that noise and rely primarily on the accelerometers to hold position, then that's what's kind of been identified for the functionality of this aircraft. Did I lose a? There we go. This is an amphibious vehicle that we've been working on with a group in Virginia, Blackbeard Biologic. The idea was for algae bloom detection and coastal monitoring. So we would be able to fly over the coast, either visually detect algae blooms or using near-infrared, that red edge band, be able to detect algae blooms, the scope, and the location of that, and then be able to go land at different locations around that and take water samples, passive water samples, so not actual Niskin samples or physical collections, but test the water for dissolved oxygen, pH, temperature, any number of qualities that sensors can be provided for that would likely be attributed to algae blooms. So you're given a ground truth mechanism for the aerial imagery that you've collected, and using that you can likely derive a model that suggests the causation for those algae blooms. And so that's kind of the project that we were working on with this. It had to be amphibious, so this can take rain and any type of precipitation, but you can see from the big hole on the bottom that it wouldn't do well if you tried to land on the water. So this system employs a waterproof camera enclosure on the front there, and we've kind of modified again the characterization of the autopilot. These are designed with pre-arming sequences that basically require them to be sitting on stable level ground in order to take off and in order to calibrate the accelerometers. So what we've done with this is we've modified the way the autopilot recognizes those values and basically diminishes that reliance so that it can be kind of bobbing in the water but still armed. That kind of tends to be a problem with these types of vehicles, and so that was our workaround for that. And then again, portability. We need to be able to take this just about anywhere, drag it out, and that's kind of what we have here. So with that, that's about the end of my presentation. I'm more than happy to take any questions on anything I've talked about here. Yes.
What are the typical prices for these three models you just mentioned?
So yeah, he was asking kind of how much do we charge for these. The market has just started, and so you see prices for equipment like this anywhere from maybe $10,000. And now we're not talking about hobby platforms, but equipment that's built out for this type of thing. And these are very unique. So fitting some of these previous applications, aerial inspection or aerial survey, you see these platforms going between $10,000 and $50,000 based on who's selling them. We sell this equipment for $15,000. Basically the way that you see it. We add the price of sensors at about $2,500, and then the software we resell also. And so an entire mapping package is right around $20,000.
Are you guys selling a lot of them, or are you guys doing a lot of the jobs yourselves? Because I know you're talking about it takes a lot for someone to know about the actual vehicle.
Absolutely. So our idea was first just to sell them, just to support people in the field using them. But what we've seen is that there is a lot of trepidation to, and resistance to getting a piece of equipment that could be outdated pretty quickly, or that they just simply don't know how to operate. And so what we're finding is the first stages is us going in and providing that service, and then after that we'll provide training and equipment for them to bring that in-house. So yeah, most of the sales right now, unless it's going to some of these research organizations, which they do that and they're typically too far away for us to provide those services, we are performing the services at the beginning. Yeah. Yes.
Neat stuff. Thanks for talking today.
Oh, absolutely.
I had a quick question about weight distribution. Looks like this last model has a camera out front.
It does.
Center. Was that an issue in some of these models?
It's always an issue if you have any kind of part of the aircraft that is visually unbalanced, because you can clearly perceive that would create a problem. And you need to maintain, especially on a waterborne vehicle like this, you could have a bottle of water hanging off one of these arms and it wouldn't affect the way that it flies. But when it lands in the water, there's no propellers that are keeping it level. So you would have it sink. And so what we did on this, the batteries are enclosed internally on this. So the battery carriage that we built that fit inside basically carried the two batteries in the back side of the internal cabin in here. So right now we have a camera in here. But we had a battery carriage that basically held both batteries in the back side, and we were able to balance it out just by moving that around a little bit.
All right, thanks.
Absolutely.
Okay, it's now to crowd. I would like to thank Sean for this really, I mean, the information that he gave us. I mean, it was really fantastic.
I'm glad.
And talk. So let's now start the pizza. And again, thank you very much for your
Absolutely. It was my pleasure.
interesting job.